Welcome everybody to our today's IMEG MSM meeting of the working group on multi-scale modeling in viral pandemics and Glimprint mini seminar. Our speaker today is Michael Getz from Indiana University, and he will discuss towards a virtual cornea. Before we let the floor open to Michael, we will do our usual welcome. Go through usual welcome slides. And especially for today, as usual, for any communication related to the working group, and if you want to get in touch with us, you can contact Thomas and James, which are the lead of the group, or James Luca, or myself, Lorenzo Veschini, for any other administrative business. And we have a communications channel, we have a Slack channel, we have a wiki page, which you can refer to. All the links you will see in this presentation are all there. So if you miss something, don't be afraid, don't worry. You will find everything on our wiki page. We have a LinkedIn page and a YouTube channel where we showcase all of these seminars. So remember, this seminar is recorded and it will be available on YouTube for later view. These seminars are also under the hood of the Global Alliance for Immune Prediction and Intervention, which is very much a work in progress, and you're very welcome and invited to help us building Glimprint. So again, get in touch with any of us to get more information or look at the website, glimprint.org. Please follow us on X, not Twitter anymore, and please retweet any other seminar if you feel like so, if you find them useful. Some announcement, there is this opportunity for Foundation for Digital Twin from National Science Foundation, FDA, NIH. And these are the details that you will find also on our wiki later on. National Academies Digital Twin Panels had happened in May, and I guess there are recording and whole information about this workshop and upcoming events on digital twin technology can be found at these links. Last, I think, we have a job opportunity at University of Florida, faculty position search, and the Laboratory of System Medicine is looking for new recruits. If you are interested or you know someone it is, please contact Rainer Lauerbacher and get in touch with them for more info and to express your interest. Some of the interesting product of the working group, Gary and Chase have put forward this new paper on arXiv, design specification for critical needness digital twins to cure sepsis, following National Academy of Science guidelines, etc. So please go and check out this very interesting piece of work. Other resource that you might find useful, a piece on Scientific American from Rainer Lauerbacher, and further on, upcoming courses about building mathematical biology tool and simulation tools. The CompuCell3D annual virtual workshop is upcoming at this date, this July and August. Please visit the webpage or get in touch at this mail or directly with James and people of the group if you are interested. All levels are welcome, and can guarantee is very interesting for anyone that want to look into that. And on top of that, something that is very complementary and is more about cell modeling, subcellular cell modeling, but very much into the soul of the group and this kind of activities. Some more publication of interest for your interest if you want to check them out. And obviously, if you have publication to share if you would like to showcase your work in under any form, we are very happy to put that on our wiki and to showcase at the earliest opportunity. So please, again, get in touch with us, mail, and or any other form, and we will try to help you showcase your work under the hood of the group, of the working group. So do we have any other announcement from anyone in the audience? Something? No? So if there are no announcements, I will let the floor open to Michael that will discuss its virtual contour towards a virtual cornea.
Today, I'm going to be showing a work that is still very much in progress. It's quite a large ask to say that you've obtained a virtual cornea. So it's in progress. So I want to show currently what the state is, what work has been done, and what findings with the current state of the virtual cornea is. This is work done in conjunction with funded by Procter & Gamble, with Catherine Mahoney on that side, and then very large input from Joel Vannon, James, and Thomas Knudsen. In general, the cornea is an interesting topic to talk about because it is crucial to vision in general, mainly, and it's vulnerable to damage because it's an exposed. It's exposed, so any incidental injury is much more likely to happen on the cornea, and its structure is extremely important. So any perturbations on the shape of the cornea, or any aberrations in even how the cornea is structured, both mechanically and chemically, can lead to adverse outcomes and loss of visions through either physical trauma, chemical burns, UV radiation, or infectious agents applied to the cornea. So traditionally, and I'm using that strongly as very traditionally, you would use a Dray's test very long ago, where you would just scratch the rabbit eyes or skin and then look at recovery. It was a very physical system, but it in the 1980s, we decided that these are very cruel and we need to start to develop alternatives. But due to the strength of the data of the Dray's tests, all these alternatives need to be compared to them to make sure that they are physical and applicable. So alternatives to the Dray's tests come in many different forms: in vitro, ex vivo, and organ on a chip, where your ex vivo are taking a recently deceased organism, removing it, and then plating it to then start your perturbational experiments on top. This can be quite expensive and time-consuming. Organ on a chip, where you basically make an artificial system of the components of the eye structure, and then see how that organ responds to any perturbation. This ends up also being quite expensive and time-consuming, although much less than ex vivo. And what I will be showing today, which are computer models, using an agent-based model simulation to predict chemical toxicities, not as a complete overhead and removal of the other systems, but in conjunction with the other system as a computational aid. So what do these virtual tissues add that aren't already there biologically? They can add multiple things, most namely, and I'm sure you've heard this before, they're fast. They're so much faster than any biological experimental network because you do not need to care and you can run them in parallel so fast. But the issue is you need to parameterize the system to generate trust. But once you've determined that, you can start asking about perturbation analysis. So you can say, how does this recover under different conditions? And you can target parameter sets that you cannot target biologically, either because there is no current way to observe the phenomenon, or it's extremely hard to quantify or visualize or determine the data biologically. You can also ask very hypothetical situations where something that is, let's say, cell-fatal normally, computationally, you can keep it alive and you can try to keep it and try to see what occurs in these situations, and these very novel, possibly never observed situations. And even on top of that, from a basic science aspect, you can start to ask from a total network construct. Biologically, you can start to probe this data that says, we think this network controls this through this through these series of interactions. Computational models, you can directly say, is this network sufficient to drive the response that was biologically observed? If not, then you can start to identify either missing arms or components, or you may have a novel protein or interaction network causing this this difference in behavior from theory to physical. So for this project, I am utilizing two different frameworks, mainly CompuCell3D, which is a cellular POTS model, but we are coupling it with Tissue Forge at certain points, which can do both center-based and vertex models. For the context of this project, we are just utilizing center-based models to create beads on a string type simulations. So before you even build a model, you have to start asking what the composition of the cornea is. Well, the cornea is transparent tissue. To aid that, it has no vascularity and internal circulation. It is immune privileged. So it has a different composition than, let's say, the skin in terms of what is present. You have a couple areas that you cannot recover. The Bowman's layer is one of them, and a couple extracellular structures that don't exist generally. And the stem cell ends up being on the peripheral of the tissue, so around the edges, as opposed to generally distributed. So component-wise, you have a tear film, corneal tissue, down into the descendants and anterior chamber. We are only going to consider certain areas because we cannot simulate the whole cornea. So we're only going to look at certain areas, the top of the stroma, the epithelium, and the tear film, along with parts of the limbus and parts in the center. So to define our system, we take a kind of generalized idea of what this interface would look like. So we have our pit with the stem cells moving upwards into flat plane to the light, and then under you'll notice the stroma and these floating cells in the medium. And what's interesting is compositionally, the stroma is a set of collagen lamellae and water creating the structure. So these aren't So they're not floating because they're in that, but this is under the assumption that the medium can perfectly capture the energy effects that these cells experience within that area, which is, you could very easily argue, depending on what the composition and structure of these collagen lamellae look like, is not the case. So to investigate this more, we started to ask, how can we represent this collagen lamellae under the epithelium? And we moved to trying to ask, can we make a beads on the spring, a beads on a string model within Tissue Forge to then allow it to communicate with CompuCell and then inform the model of what the tissue composition is to then affect the energy acceptance rates of these movements. So here is a very sparse beads on the spring representation for the domain, and then the direct read into CompuCell3D done through by spatially binning the fibers. So now that we have this fiber orientation into CompuCell, how do we allow it to affect the movement? These are large fibrils at about 30 nanometers that are really composed of multiple fibrils. They're quite large and could very easily provide impedance towards cell movement. So if we say as a simple system, we say everything is very well aligned, our bivector is straight across, straight on the XY, the X, but we have a movement not along that plane. How will the cell react? So this is it's much more straightforward when you try to think this in terms of a center-based model, since they are all handled in vectors. But when you move it back to a smaller domain solver, such as a CompuCell, the waters are muddied a bit. So you have to start to look at, just as you would with the center-based model, is what are the components that are aligned and orthogonal? But then you have to ask, how does this accept my energy acceptance rates? And there's two general ways that you can do this, where we moved forward with one, but it could be very easily argued that the second is also a perfectly valid model. So the one that we've moved forward with currently is a deflection of the target pixel. So we take the orthogonal component, and then we reduce it relative to anisotropy to make a new vector, which then selects a new a pixel that you do the computation for acceptance with some energy reduction due to the deflection angle, which you can see if we say that anisotropy or the alignment of the fibers is not perfect, so the cells can slip through this barrier formed by the lamellae, then you'll see a 50% reduction in this case, just giving some random value in the vector, so you get less movement in the y plane for this case. The other option that you can do is very natural to CompuCell, and has been done before, is a flat energy penalty. And this is, you would generally take how big the orthogonal vector is, and then apply a energy penalty towards acceptance dependent on that value. Other methods that you could do are that this network is physically applying force, which is a very good way to handle it. The issue is, especially on the scale that we're trying to deal with, it's very, very expensive. So once you do that, you can see for an isotropy case, the cell will start to align with the fibers and will really only move along the X-plane and kind of spread itself out as it moves down the plane more in order to try to retain its volume energy. We can also add other interactions with CompuCell and leverage its use of chemical fields and cell positions, such as adding a chemical field, which then can destroy fibers, which will be very useful as in a couple slides. And we can have cell deposition, so you can have fibroblast deposition of more collagen fibrils, which could then contribute towards the alignment of these fibrils. You can also have combing, which we do have combing, but we don't have, I don't currently have it shown here. So we can then start to probe this combined CompuCell model on the injury type that you'd expect between no injury type, which is a very simple recovery, a slight injury type, which really only gets into the superficial and wing cells, which are the top levels of the epithelium, and mild, where you can get near the Bowman's layer, but the Bowman's layer is still intact, and a moderate, which breaches the Bowman's layer, and then you start to reach the stroma. And a condition that we don't consider, just because there's honestly no point, is a severe, which is it rips through all the layers, and we don't consider severe because there is no recovery, and we're concerned with recovery and then trying to figure out what type of recovery we may expect.
Michael, you have a question in the chat?
Sure. Yes. That is not shown on the on these cases. Sorry, it's not shown on these cases, but we do have combing. So that would be combing, the cell moving through these fibers, especially misaligned fibers. I mean, it only occurs on misaligned fibers, of course. It will realign the fibers according to the cell movement. So another point of interest is the basement membrane. And this ends up basically being this great filter preventing the allowance of TGF-beta, FGF, and PDGF ILB1 into this stromal layer, which is of importance because these keratocytes within the layer, when they start to detect these components, for keratocytes, namely IL-1B or your pro-inflammatory component generally, will start to allow these I mean, they're fibroblasts, virtually, to start to differentiate into fibroblasts or activate non-fibrotically. So it'll form fibroblasts and myofibroblasts once this barrier is breached. So you can almost approach it as a signal source. In terms of our initial conditions, we can see visualized what a slight, a mild, and a moderate may look like. Slight is a very shallow, not touching the basal. Mild gets near the epithelial basement membrane, and moderate will sever the epithelial basement membrane, getting the stromal response. So the first two, slight and mild, I'm going to show a simulation that only shows the epithelial layer because the stroma is irrelevant in those cases. And then the moderate will see the combined model of both the stroma and the epithelium. So after a slight injury, you'll see the system will recover very fast. You'll get the small abrasion, and then you get basal cells creating new wing cells, and the superficial cells regrowing to their normal level in fast succession. Similar to mild injury, you'll get a deep injury forming right here in a second, there. And then the basal cells will start to fill out the missing area, the wing cells return, and the system fully recovers. In this case, it takes a longer period of time due to the fact more injury has occurred. So then we can start to probe the combined model, which is your moderate injury, and then see how do these fibroblasts and keratocytes. In this case, it's important to note that we only make a distinction between keratocytes and fibroblasts, which means that in the current model, we only have a fibrotic response. So this means we will generally always have an unfavorable response under moderate injury, because you will have collagen deposition. So you see the same thing. It'll reform the epithelial basement membrane, which is these green lines, and the basal and wing cells reform. And for each component, surfactant, which kills the top level, EGF, TGF beta, which are supplied through these green tear cells on top, and PDGF and IL-1, which are the activating chemicals for what's effectively immune cell fibroblasts in the stromal area. I won't go through this network very detailed. We currently have a simplified representation of this network, where we just have activation and differentiation dependent on IL-1 beta presence and PGF, where complete loss in those components will cause cell death in order to allow a turnoff, or we allow for proliferation upon receiving the activation signal to bolster the cellular response. In depth, cell proliferant differentiation and death in the epithelium is done dependent on a few different papers, and generally what you'll see is the stem cells will create in the limbal region. They're allowed to make more stem cells. Once they leave into the peripheral cornea and into the central, they'll differentiate into your basal membrane, your basal cells, which will then be allowed to leave the basement membrane, form wing cells, and eventually form superficial cells when exposed to the top layer as they're squamous. And this is very robust, at least this simplified interaction, because it will, given stem cell presence, it will regenerate the whole limbal and periphery area. But what's important is this dictates stem cell presence. Without the stem cell, the system is not as robust. In addition, going back to the idea of the epithelium basement membrane as a barrier, it's very easy to see conditions where this epithelium basement membrane isn't redrawn. Purple in this case is your is your Bowman's membrane, which is different than your epithelium basement membrane. You see that a continued signal source causes excess growth of the keratocytes, myofibroblasts, and fibroblasts. So this is definitely going to form a fibrotic response, which is unfavorable because excessive deposition of these fibrils into the local region causes either deformity, which then leads to loss of opacity, or just the sheer presence of these cells in that local region, especially late level differentiated versions, like myofibroblasts themselves cause opacity loss. And due to the fact that we only have fibroblasts in this case, you can have cases, you can have certain circumstances where these fibroblasts will start to wander into the epithelial level, start to deposit this more epithelium basement membrane, and the system can't effectively form a level ground, and you get something reminiscent of incidental ectopic fibrosis, where you have these basement membranes being built into the epithelial space, which is definitely not good. In terms of next steps for this model in general, is we need to expand the role of these keratocytes so that they are now activating in a non-fibrotic way, because when they activate non-fibrotically, they can reform this epithelial basement membrane through depositions of components like nitogen 2, and then stop the infiltration of these activating components, thus decreasing the amount of fibrotic deposition and possible loss of opacity. We need to also introduce donor cells. Just because the area is immune privileged does not mean that we don't get your typical immune response in the area. And we need to develop a low-cost fiber representation. The issue is with these fiber networks, they are still very expensive. In most cases, we're decoupling the tissue forge model because the solving for what is almost effectively solving for all of these beads on a split string and then moving them back and forth into CompuCell3D, where currently a lot of the cost is moving across these frameworks, slows down the system immensely, and it would take multiple hours to get a single simulation solution. So that's not good. We don't want that. And that is currently what I have. I think I ran through very quickly, so I want to acknowledge Joelle, Catherine, James, of course, Thomas Knudsen, and in general the Glazier Lab, because they definitely have to deal with me rambling on about something weird quite a bit. And thanks to the funding from Procter & Gamble to help aid in this work.
Great talk. I think it was very interesting. Let's see if there are any questions. Please feel free to raise your hand or unmute yourself and pose a question. If you are unable to do so, just let me know and I will unmute.
So I see a question from Yi that I missed. So the data that we have for model validation is going to be the data that we're getting from Procter & Gamble through this collaboration will be ex vivo pig cornea. Although they are looking at more typical cells on a chip for some of the epithelial perturbations. The data for a lot of the validation, especially some of the questions, are still being generated, along with some of the methodologies that are being refined. Yes.
So sorry, great talk, Mike. This is Yi, and my question is related to do you have time sequence? Do you have for 3D structure? Do you have chemicals in addition to the cell images? Do you have the fiber alignment? What level of details do you have?
So you can, from literature, you can get some of the data, though it's not exactly sufficient. So in terms of data that we can procure to get to evaluate this model, we can get fiber alignment. We can get a 3D structure through NMR, and the chemical reads generally for a time course would be hard to achieve. So I'm not exactly sure what level of data we can retrieve from those, saying unless it's readily available through something like a wash, which means it would have to be in the tier layer. We're dealing with having to basically lyse either part of the system or a whole system, as I understand it, to get the deeper level chemical outputs, unless we leverage something like a fluorophores that would be non-destructive, as opposed to blotting in that case.
So your comparison would be the wound healing process as a function of time to your model system?
The most apt comparison would probably end up being opacity per time, although that is deeply connected to recovery. The issue with some of the ex vivo, especially in long time periods, is you can't get the total you can't get the total response because it is ex vivo, so you're not getting the kind of reconstruction that you would expect, or you're not getting the pressures that you would normally get on the surface from the aqueous humors. So because it is removed from the system and it's ex vivo, observing long-term recovery currently doesn't seem to be possible.
Mm-hmm. So how do you translate your cell structure into opacity?
So that's actually one of the I would call it an open question at this point, but it ends up being a combination of the fiber alignment, the cell presence, and the water content in the area. But because we're not exactly sure to be certain on what exactly that function would look like.
Mm-hmm. Very interesting. Thank you.
Rita, I think, has a question. Please, Rita, feel free to unmute yourself and pose your question.
Thanks. Michael, thank you for the great talk. We are starting a collaboration with Joe and James, and we are working on the expression on cornea cells from the atlas of cornea cells, human corneal cells. And we are especially focusing on the possible interaction between them. So because we are in the very start of this study, would you have some suggestions for us on something that we should focus on?
I mean, I've been in those discussions. So outside of what is given, I don't have much to add on top, I guess.
But what kind of cells, of cornea cells, they should interact? What kind of interaction they should have? That you expect them to have? What would be something that would help you? What would be something that would surprise you?
In terms of aid, trying to in some way determining the role of the donors versus the residents cells in terms of response would be extremely helpful. There's only certain types of macrophages that are present. I think it's CD4 negative, which will then later recruit an active version of the macrophage, along with the normal cascade. But what I haven't seen determined, and it could be I haven't looked strongly enough, is what exactly what is the relative difference in terms of non-fibrotic recovery when you utilize only resident or only donor cells, or even what is the expected presence of donor cells after a signal source.
I will present, maybe we should talk after that, together with Joe, of course. And then we could discuss on the map of the different cells that you have in Atlas. And so what would be the interactions or that we should expect? Then I will schedule some talk for us if Joe is okay with that. Joe, are you okay?
Yes, of course. Yes, of course.
Okay. So we have another guy working with us that we will start now, which is Gustavo. And Gustavo is now he ended some tasks he had to perform until yesterday. And then he's starting to the analysis of attacks. He is SEC. Okay. And we are going, but we have to know more or less what we are looking for. So that would be good if we could have some talk with Michael, you, Gustavo, and Rodrigo. Okay. Yeah. Rodrigo is another Brazilian guy, Michael. Brazilians are everywhere, you know. Yeah. Okay. So that's it. Okay.
Thank you. Rita. Yeah, we can set up that meeting, and I can let you know a little bit of what I've been seeing, what is already introduced in the model, what we want to introduce in the model, and to see if we can confirm from that data.
Yeah, and because if we know what we are looking for, maybe that things will help us to look for the right things or for the right signals. Okay, thank you.
Thank you.
I have a question.
Yep, please, TJ, go ahead.
Thanks. First off, Michael, great talk and great work. I mean, I'll say for anyone here who's not familiar with the technical work involved to do simulations like this, I've worked on this in the past and continue to do so. And I I mean, what Michael's done here involves a lot of technical work. So just doing these simulations in general, combining these methodologies is really an impressive accomplishment. So want to make sure that that's properly acknowledged. That being said, I mean, Michael, like with including the extracellular matrix, I mean, obviously ECM is complicated. And you know, you have what currently seems like some, you know, somewhat generic representations of some of the mechanical roles that you know, ECM may or may not be playing here. And I'm curious to get your impression of like the perspective concerning what complexity to do with the extracellular matrix, whether it be biological or mechanical or otherwise. You know, what roles are missing in your model that you suspect might be important, and of those, what challenges do you anticipate in terms of potentially incorporating some representation of those mechanisms? You know, is it issues of data availability or computational costs, just sheer difficulty of making two software packages work together? How do we get a better ECM representation into this model?
Yeah, that is a loaded question, to say the least. So to be honest, the big barrier that I see is computational cost. Just at least in the way that I'm currently approaching it. To move this representation to say 3 dimensions, it gets absolutely untenable. To get to also have that with a good density of the beads on the string, and have it talk in and out of CompuCell, which is exactly why I've been doing more generic approaches. I've been trying to see how much can I get away with, and then add complexity as I go. Currently, for the larger simulations, it is only a vector representation, and I don't have it going into the tissue forge layer, because it crawls to a halt. And we can talk about it at some point, because I'm sure I mean, you're free to yell at me for things that I've done that are not
we can talk
computationally cheap. But it's the real big barrier right now is simply computational cost. But you can look at like very complex representations, like Roland Merck's. I'm hoping I'm getting his one of his papers that he came out. He has this very intricate ECM network putting pressures on a single cell or 2 cells. And they have claims that itself is pretty expensive. That's a pure energy representation. And ideally, if I could get that representation on this tissue size, I would. But it's way too expensive.
Sure. Great. Thank you, Michael.
Great. Are there any other questions?
Maybe very briefly, Michael, if you could just say how you shared data between Tissue Forge and CompuCell. Was it manually, more or less, or did you adopt one of these frameworks?
So to great credit to TJ, the Tissue Forge has a very convenient Python API. So since CompuCell3D is in Python for a lot of the facing pieces, I just had it talk to the Python API. There's also a C++ API, so I could think about moving it there at some point. But currently it's using the Python API, and then I'm actually using, I'm spoofing the data down to the C++ layer by telling the system that they're CompuCell objects that aren't used. And then I have it directly modify the core cellular POTS mechanism.
Okay, thanks.
Any other question? While perhaps something comes up, I have a curiosity for you, Michael. You have shown, I took that your stem cell in the model, they seems to be restricted to the lateral area, the limbal area of the cornea. Is that right? I took it right? And if so, I wanted to ask you if that is a case that you take from the physiology, or if something that is a convenience for simulation purpose.
So it is physiological, but it's also a sort of due to the I mean, quote unquote toy nature of it, since we can't get the full complexity of the corneal shape. The stem cells are only around the periphery, so you only expect them at the edges, and then they move in. If you want a neat paper, I would ask Joel. He was showing me this very interesting paper lately that I can't remember off the top of my head. Sorry, where they show how the stem cells at the edge need to be placed to fully form into the center of the structure. But yeah, they are only around the edges. It's not something like where you'll see multiple pits that contain stem cells. It's a pretty defined structure.
So it's not like the skin where there is a basal layer that they decide who proliferates, who not, who is stem.
Yeah. Yeah, it's different. It's distinctly separate from the skin in that fact.
Spatially organized in that way. That's very interesting. Okay, thank you. Is there any other question from the audience?
Really awesome presentation, Michael. I think it's going to take me a while to digest everything you're doing. It's pretty complicated.
Or maybe I do a better job explaining.
That was good. Okay. If we don't have any other burning question for today, I think I will lead the meeting to a close. I would like to thank you all very much for coming up today. Thank you, Michael, for the very nice presentation, sharing your work with us. I guess there is a lot of ground for discussion and for collaboration.